Polyonics, Polymer Materials for Electronics. Polyonics presents a study in the ESD risks associated with process-required labels and tapes used in electronics manufacturing. Electrostatic discharge, or ESD, occurs when a static charge is released in the form of electrical current into a static-sensitive device. If the charge exceeds the specified thresholds of the device, it can cause immediate or latent damage. The ANSI ESD S20.20 standard and its international equivalent, IEC 61340, define the ESD control plan required to help prevent ESD damage to static-sensitive devices. Within the S20.20 standard is ANSI ESD S541 that governs process-required insulators such as labels and tapes when used in the proximity of static-sensitive devices. ANSI ESD S541 requires labels and tapes to have surface resistances greater than 10 to the 4th and less than 10 to the 11th ohms to be considered static dissipative, and have charges no greater than 125 volts when used within 1 inch of a static-sensitive device. The following ANSI ESD standard tests contrast the differences between Polyonics non-ESD and ESD Safe labels and tapes.
So I'm going to start by testing XF440, a non-ESD material. ASTM D257 specifies a 1-minute electrification time, which means I theoretically should wait about a minute, 60 seconds after I apply the voltage to take the measurements. And you can see after a period of time the numbers settle down, and that's why we're doing it that way. Take the average of that measurement is 8.86 times 10 to the 12th ohms. And we can compare that to this material, an XF446 ESD material used for, again, label materials. Normally I would start at 10 volts, and STM 1111 specifies using 10 volts for materials that are more conductive. But I pre-measured these materials, so I know that they're above 1 times 10 to the 6th, and this is one of those materials. It's just a little above 1 times 10 to the 6th, but it still means I need to use 100 volts bias. My average of for this material is 4.04 times 10 to the 7th ohms. So clearly it falls into the range of static dissipative as specified by the ESD Association. So now we'll move into the tape material. This is XT620 for non-ESD material, which we'll find out here as we measure it that it's an insulative material. In this case, this is 3.3 times 10 to the 12th ohms. Surface resistance, again, it falls into the insulative range for materials. XT622, which is an ESD material. Again, because drop my voltage down to 100 volts. And now I can calculate my average. In this case, this is 1.9 times 10 to the 8th ohms. This material. So clearly, again, falls into the static dissipative range. I'm going to start by measuring the voltage on a non-ESD tape material. Just for reference, I am grounded and I'm using static dissipative tweezers. Okay, I'm going to start with a non-ESD material. I'm going to start by measuring the voltage on the tape after I peeled it off the liner. And as I measure the voltage on the tape, you can see it's in excess of 7,000–8,000 volts. I have trouble getting close enough to the probe because it's pushed away by the static field. There's such a high electric field there. So now I'm going to test a material that's an ESD tape material. Recall the last time we did this, we had 7,000–8,000 volts on the non-ESD material. It's an ESD material, so very little voltage left on the tape. Now I'm going to apply the tape actually to the board. And I'll measure the voltage on the tape as it sits on the board. And you can see here that's basically 0 volts. So clearly the ESD tape has an advantage over the non-ESD material. Peel this tape off and measure the tape, voltage on the tape again. Again, clearly differentiates a dissipative material from a non-dissipative material used for tape applications on printed circuit boards. I'm going to start by measuring the voltage on a non-ESD label. So the first thing I'm going to do is I'm going to attempt to peel the label from the liner, and we're going to look at the voltage, measure the voltage on the label, and you can see I'm measuring several thousand volts. Show the voltage on the liner, which in this case I'm measuring minus 7,000 volts. So there's significant voltage on these materials, and they're not bleeding off through the tweezers and through me. Now I'm going to show the voltage that's retained on an ESD label after it's peeled and applied to various components as well. So as I peel the label off, I measure the voltage left on the label after it's peeled, and you can see that it's almost negligible in the 30 volt range. Materials that it would be safe to have on an ESD Safe workstation. So now I'm going to apply this ESD label to a board. I'm going to make sure I got an edge over, because I'm going to peel it off here in a few minutes, but I'll rub it, make sure that it's adhered to the board, and now I'll measure the voltage on the label after I've rubbed it. Almost negligible. Now I'm going to apply the label to a plastic epoxy package. As I again measure the voltage now on the label as it's on the part. You see almost negligible voltage is left on the label material. And now to simulate a rework, I'm going to peel this label material off of plastic package and measure the voltage on the label again. What's significant is the difference between, in this situation, the ESD material and non-ESD material. We measured thousands of volts on the non-ESD material and only a few volts on this, negligible. And the reason being is the material is dissipative and it's grounded through me, so any charge that's built up is bled off through me.
These tests show that the Polyonics static dissipative and low charging labels and tapes provide safe and reliable solutions that help prevent electrostatic discharge on static sensitive devices. Their surface resistances are within the S20.20 specified 10 to the 4th and 10 to the 11th ohms, and the charges they accumulate, including their liners, are well below the 125 volt specification. Polyonics ESD-Safe labels and tapes, proven valuable elements within successful ANSI ESD S20.20 and IEC 61340 control plans. Polyonics, polymer materials for electronics.